Welcome back to the workshop for one last video on a matching problem. All right, so we talked about the 7 brides for 7 brothers, and we figured out how many different ways there are to pair them up. A lot, by the way. And we'll talk a little bit more about what it would take to test those matchings later in a later section. For now, we just want to also continue talking about counting things. So let's take a look at a couple more examples. All right, a permutation of a set of objects is any ordering of those objects. So when we talked about arranging these 7 brothers, we're talking about permutations of those brothers. So to make a little bit more simple example, we want to determine the number of permutations. How many ways can we arrange 3 people, Alonzo, Bartholomew, and Caesar? And then we want to give all the permutations. So we said, using this counting principle, that the brothers we could rearrange in 7 factorial ways. And here it would simply be 3 factorial, which is 3 times 2 times 1. Now you may have found that by saying, oh, I need it to be choose 1 person, 2nd person, 3rd person. There's 3 options, Alonzo, Bartholomew, or Caesar. Then once I choose one of them, I only have 2 options. And then once I have chosen 2, I only have 1 option. So that's exactly right. This what we said it was, 3 factorial. So whether you found it this way or simply recognized pattern recognition that it would be 3 factorial this time, either way is fine. But 3 times 2 times 1 is 6. And so there are 6 ways. Now, maybe you said, that's not how I figured it out. I figured it out by listing them all. That's a really terrible idea, mostly because if I make that number 7, can you list out all 5,040 ways? Ooh, that's a little tough. So you want to be careful about that. But we do want to be able to recognize that this is correct. So with this small example, let's see if we can list out all 6 ways. So listing them just with the letters A, B, and C, we could start with exactly that, A, B, C. There's 1 ordering of the 3 people. I could also do A, C, B. Okay, let's see here. I could do B, A, C, and B, C, A, and C, A, B, and C, B, A. There we go. How did I decide to do all of those? Well, mostly just alphabetical order, right? Starting with all of the permutations that start with A, B, C, alphabetical order. And then the only thing I can do is swap these 2. Okay. The next would be starting with B. So alphabetical order, starting with B, and then alphabetical order, A, C, and then swap them. C, then alphabetical order, A, B, and then swap them. So that gives us our 6 permutations. Excellent. So those are permutations. So in general, if you hadn't noticed it already, like I initially stated, and you did the multiplication principle for counting, that is absolutely perfect. But now we want to recognize that in general, there are exactly n factorial ways in which we can order n objects. That is, there are n factorial permutations of n objects. All right, so let's take it one step further. Let's suppose that we want to choose a president, vice president, and secretary to be elected from a club with 12 members. How many different ways can we elect this president, vice president, and secretary? Well, I need to choose a president, a vice president, and a secretary. So I have 3 choices to be made in this. I have 12 options. Then I have 11 options once I've chosen the president. And then I have 10 options once I've chosen a secretary. So 12 times 11 times 10 gives me 1,000, right? 12 times 11 times 10 is equal to 1,320 different ways. Okay, well, is that really all that we wanted to take away from this example? No, we can actually write this using factorials. So kind of dropping down here, I can notice that if I wrote this as 12 times 11 times 10, right? 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and then divide by the same thing. Well, that was just 9 factorial, so I could have written 9 factorial, and that would have been fine. This gives us 12 factorial divided by 9 factorial. But we can take it one step further. It's 12 factorial, which is 12 is the number of people we have, divided by 12, the number of people we have, minus 3, the number of people we're choosing to order. How many ways can we order 3 of the 12 people? 12 minus 3 factorial in the denominator. So this is the thing that we're looking at. The answer to this specific problem was as simple as that. But what we wanted to do is observe that we could write that answer in this way, which allows us to say that the number of ways an ordered list of R objects can be chosen without repetition from N. So no repetition here, right? We can't have the same person serving as president and vice president. The number of ways we can list 3 distinct objects from, or list 3 objects from N distinct objects. Well, N minus 3, but in general R. This would be, we have N objects, and we're going to permute R of them, so N minus R factorial. Now this has a convenient notation. This is denoted by a couple different ways to do it. NPR is one way to denote it. Another way is permutations of N choosing R of them. So both of those notations are perfectly appropriate. But that's it. That's it. Those are the counting methods that we wanted to discuss. Again, there's a little bit more on creating lists, creating subsets, and that sort of thing, actually in section 1.4. But for now, that's all. So thank you for your time and attention. I'll see you guys again later back here in the workshop.